All right, you're at the session Amazon on Amazon, how Amazon designs chips on AWS. Thanks for attending. My name's Chris King. I'm in the Annapurna organization in AWS, F1 engineering manager, and also manage the EDA infrastructure for the US infrastructure. I'm really excited to talk to you about how we do it. And I'm going to also talk about what other partners and EDA vendors are doing on AWS. But the main focus will be how we build our silicon and how we use our own AWS infrastructure to build that silicon. So a little quick agenda. We're going to go over EDA development in the cloud, go over some basics, go over the internal AWS silicon development, talk about some of the managed services that can be used for EDA, and then also the AWS EDA infrastructure, a quick demo or a little sneak peek at an upcoming workshop that we're going to do. So related breakout sessions for this week. We have CMP 405. It's a accelerate your C and C++ applications on EC2 F1. This is a workshop where 2 hours and 30 minutes, you're going to learn how to use the F1 instance. I think this is pretty valuable for this audience to know, because what we're going to talk about later is how you can use the F1 instance for EDA. One thing is IP emulation and verification acceleration. So I'd encourage you to look at this workshop and see if it's interesting to you. That's on Wednesday, November 28th. On Thursday, we're going to actually do the EDA infrastructure workshop that kind of relates to this session. So my team has put together a workshop that will pretty much build an EDA infrastructure out of the box for you. We've stripped down our internal templates and infrastructure, and we have now are going to be providing it to you to build an infrastructure in that 2.5 hours and run a simulation and see the scale of AWS. It's going to be a really cool workshop, and I hope you'll attend. And that's on Thursday, 3:15. Okay, so as we all know, the semiconductor industry is a very complex industry. So it starts with kind of the design specification and predicting what your design and features need to have, and your specification and architecture for 2 to 4 years out. And then designing your chip, designing your IC, and then verifying it, making sure it doesn't have any bugs, and then paying $10, $20 million to get it manufactured. Just there's a lot of opportunities and challenges and opportunities for improvements. We see that the cloud can help look at those opportunities and challenges differently, and we can use some of the AWS Managed Services to do that. And then continuing on, you got chip packaging and assembly and product integration, which as we continue down this path of moving to the cloud, we'll start to see those stages in the semiconductor development be automated and improved by using the cloud. So your on-premise EDA infrastructure today, you have a lot of questions that you need to ask yourself, and I think these are important things to think about. What servers should you buy, and when should you buy them? How many do you buy? What are your needs going to be throughout the design cycle? If you're doing gate-level simulations, how big of servers do you need for these gate-level simulations? How much memory? When do you need them by? Your design cycle may change, and you may have purchased them too soon or too late. And then, what's your throughput of your compute and storage? And how fast can you get new compute and storage when you're working on premises? And then, how do you protect your IP? That's one of the most important things about our semiconductor industry, is the intellectual property that we create, and how do we protect it? Capacity planning, as I've already said, we need to make sure that that we're ready for that peak when it hits in the development cycle. So network latency, how do you know that your networked file system is going to be able to support the billions of cycles that you need to run? How do you know that your shared file storage is going to be able to handle millions of small files being written and read at the same time? So, and also, how are the third-party EDA licenses work in your on-prem and used by the different teams in your organization? So before we get into answering all those questions, let's start with some basic vocabulary. I understand most people here are probably from the semiconductor industry, but just in case you're not, let's just talk about it because I could use these terms and you may not know. So, fabless semiconductor company. So Amazon is a fabless semiconductor company. We don't own a fab. You just saw that we released a new chip, a new A1 instance type based on our own silicon. So there's other examples of fabless semiconductor companies: Qualcomm, NVIDIA, Broadcom, Apple. This is a very common method. And then there's the semiconductor foundry, which is actually what manufactures these chips. Next is the integrated semiconductor company. This is more like the big companies that have fabs. Intel, used to be AMD. And then you've got the electronic design automation. This is what we call EDA. This is the software and the synthesis and the tools and the infrastructure that allow you to develop these chips and allow you to develop the silicon. And then you've got your intellectual property. We call it IP. This is what you want to protect. This is what's yours. This is your secret sauce. And this is sometimes what you license to other companies. So let's go over some of the challenges and work our way down from the top. So the first, if you can break it down into three distinct phases in the development cycle. You got the front end, the back end, and the product and test, the post-silicon. Breaking down the front end, you've got design specification, trying to understand what are your needs, what does the product needs for 2 to 4 years out. And then taking those needs, putting them into a design, and then verifying that design, making sure that there's no bugs, and then making sure that it can physically be laid out and created in the fab. And so there's lots of challenges in just the front end. Billions of simulation cycles. So one of the things that some companies use is they use metrics to determine when they're ready to tape out. Those metrics could be that I've hit a certain verification coverage, that I've hit a certain billions of cycles during my design bake. But those billions of cycles take a toll on the infrastructure, and the infrastructure design can slow those cycles down, which slows the development. So we've also got millions of small files are being created during these verification, simulation, and verification runs. There's also a high level of concurrency when you're running thousands, tens of thousands of jobs all at once. And that equates to a need for a high-performance storage. The storage that we see is a mix of random and sequential I/O for the front end. And it's very taxing on the storage system when you're running these simulations. So there's lots of challenges on the front end. Now let's move to the back end. So the back end is large files, very sequential accesses, and large memory machines. One of the questions I asked was earlier, when are you going to need these big machines for gate-level sims, GLS? And how big a memory are you going to need? So that's a big challenge. Your verification team could say, I'm only going to run 10 tests for GLS. And then they could change their mind and say, we found a bug. I really need to run 100. And now you've got a big problem. Now you've got to be able to find 90 more terabyte machines to be able to run these simulations. So the back end has significant challenges. And then, as we know, the production and test, you do a lot of stuff pre-silicon before silicon comes out to prepare for post-silicon production and test. And so those things are incorporated in some of the front-end testing and the preparation. So definitely a lot of challenges in the chip development that when you make changes to your infrastructure or you have an infrastructure, it can significantly affect this development cycle. So a lot of the front end has been worked on in the cloud for a number of years. There's a lot of partners, and we'll talk about those partners. But just recently, there's been a major announcement, and that's TSMC has announced that they're supporting the cloud. And the cloud is pervasive, and it will be fundamentally influence the silicon design. TSMC is the first foundry to collaborate with design ecosystem partners and cloud partners to enable designs in the cloud. This is huge. This pushes the cloud adoption down the development cycle farther down as we make our way from front end to back end to post-silicon. So let's go back to the front end a little bit more and talk about what some of the partners are doing to enable cloud development. So Cadence has got kind of two paths here. They've got a fully managed path on the right, and then they've kind of got we'll support you in your own cloud path. And this is a very good start from Cadence, and we expect this to continue to grow. And I think this will continue to enable companies to build in the cloud. And then Synopsys is starting to release more and more support for the cloud. They have a similar approach where they have a customer managed, where they provide scripts, support for running in the cloud. And then they've got a Synopsys managed option. And then they also have the emulation managed option too. So a lot of adoption from our EDA vendors, which is starting to help this movement to the cloud. So let's talk a little bit about some of the partners that are migrating to the cloud and how they're doing. So in 2010 or 2012, NXP has started to migrate to the cloud. They've built up a significant R&D IT dedicated team to work in the cloud, and they've been a partner with AWS to build out their cloud infrastructure. And we really are looking forward to seeing more and more of what they're building and hear about their progress. Next is Xilinx. So Xilinx and AWS have been partnered a lot over the last couple of years. One is F1 instance. We partnered with Xilinx to build the F1 instance, and in that partnership, we learned from each other. We learned about FPGAs. Xilinx learned about working in the cloud and the AWS services. So since that partnership, it's generated Xilinx running some of their regressions and overflow into the cloud. You've got instant access to the right compute and memory for their jobs, and it's reduced their development cycle time already. Another one is MediaTek. So MediaTek has been developing in the AWS cloud. They've been working with AWS for some time now, and we're happy to see that they've gone through a full development cycle on AWS. Okay, so let's talk about some of the AWS Managed Services that are useful for EDA. So I'll spend a little bit of time on this chart, and then we'll go and we'll break it down more, into each pieces. And I'll focus on how these are used in EDA and how we use them for our custom silicon in EDA. Oops, sorry. So first is automation and orchestration. So there's two main pieces here: AWS batch and CFN cluster. So AWS Batch is a majority kind of a container-based approach. It spins up instances dynamically for you and orchestrates the dynamic up and down of the instances using ECS and Docker. And it's very powerful. It's what we use internally, what we're going towards internally. And we feel that it's kind of the direction of the future for running simulations and back-end jobs. But we also see a very important need for CFN cluster. CFN cluster is a framework that allows you to utilize your current scheduler and benefit from dynamically scaling in the cloud. So using SGE, SunGrid Engine, to immediately just start taking advantage of scaling up and scaling down. I think this is a great short-term benefit for using the cloud and scaling out into the cloud. They're making a lot of improvements to the CFN cluster tool, and I think it's something you should consider in your plans, in your short-term plans. I haven't used Nice Engine Frame yet, but it's definitely an option to consider. So that's the automation and orchestration. I see batch as the long-term approach for us. We are going to containerize, and I'll show you a little bit more about that later in the presentation. Storage. So storage has been a key for us. We've spent a lot of time benchmarking storage options. We even built our own kind of benchmarking model of what a simulation looks like to a storage, to a storage cluster or NFS server. We did this because we wanted to be able to share the behavior of that benchmarking model with the internal teams. And by sharing it with the internal teams, we were able to get their feedback and help them improve their service. And so we built this model. We've benchmarked some of these these storage options, and we feel that there's actually a good combination to go with for development. We look at our workflows and our storage needs, and then we categorize them. So we focus on like transient data and non-transient data. Data that changes very often and data that stays pretty much the same. Give you an example. Non-transient data is tools. Tools don't change very often. I mean, you upgrade them every now and then, but they don't change that often. Transient data is regression results, builds. They change very often, daily, weekly, hourly. And so we've categorized these types of workflows, categorized these types of data, and we've put together the storage option for each type in each workflow. And so EFS is very important for us. We may use it for home directories or tools directories, but then we put together maybe a more different solution, an NFS type solution for where our simulation results go. And so we've built up multiple storage options to be able to build the optimal kind of architecture of storage. And then S3. So S3 is actually where we feel we want to go long term. We want all data to really reside on S3 and restrict what needs to be on a networked file system. And scrutinize what goes on a networked file system. So, for example, we have new projects where all the regression data goes to S3. The user, it takes the user an extra step, but they have to run this command to pull the data down to S3, maybe the failure. Maybe we have some automation that pulls the failures down automatically to a network file system, but a majority of the data is on S3. And that helps us with a lot of problems with storage and storage, maintaining large amounts of storage and data, and understanding when we can when we can remove data and when we don't need it. So S3 has a very good kind of life cycle for that. Compute, so this is the heart of it all. So this is your development cycle is dependent on your compute. Since you run billions of cycles, we look constantly for the fastest compute. And that's the great thing about AWS, is you get access to the fastest processors, the fastest servers, and you don't have to spend the money to upgrade anything, any hardware. It's available to you right away. So Z1D, you've heard a lot about that. We'll talk a little bit more about it. We've started using Z1Ds. We see up to 30% improvement in our simulation times with Z1Ds. I highly recommend it. Z1Ds were built with a certain memory and vCPU ratio, and we helped with that ratio and gave them feedback, and we feel that it's a good fit for our compute needs. FPGAs. So FPGAs have a really niche place in the development cycle for silicon, and it really depends on your design and how much FPGA size you want to purchase. The F1 instance, I think, fits really well with IP emulation and some validation usages. So you just heard from ARM. They released a reference board in the cloud, is what I'll call it. Essentially, you now have access to an ARM processor in the cloud, and you can develop for that processor in the cloud. So we feel that the F1 instance for our projects is very powerful, and that's where F1 came from our internal development and our internal expertise on FPGAs. So compute. We also, make use of auto-scaling, but we also make use of it through the batch. Visualization is important. We use, what's not listed here is some of the things that we actually use, but nice DCV is a tool that's out there. We don't use it, but I think it's very powerful. But we are shifting to workspaces, Linux workspaces. But currently, we use a combination of an RDP-X11 and an NX server. So networking, very important, enhanced networking. We look at all ways to get that biggest bang for the networking speeds. That's one of our, when we architect an infrastructure, we're always looking at what our instance types and the networking bottlenecks. And ISVs, I see that this in the future that we'll see a lot more partners, a lot more people, ISVs and partners on AWS Marketplace that offer IP and offer tools and more EDA tools. It's coming soon. I think it's already starting with ARM. Xilinx has their tools up there on AWS Marketplace, and we'll see more and more in the future. Okay, so let's break down the compute families and how they relate to EDA. So first, on the far left, we've got the general purpose. I'm sure you guys are all familiar with these, but I'll just touch on them really quick. So we've got the general purpose. We've got the compute optimized with the C5, C4, Z1D. And then we've got the storage and I/O. The I3 is the key one there that we use. And then the memory optimized. This is your GLS, your big memory machines, SoC type simulations. And then you've got the GPU graphics and the GPU and FPGA compute. So now let's overlay what EDA workloads fall into these categories. So we typically use the T2, M5, M4s for these service instances. I listed license servers as an example, but these are instances that are always up and running. They're doing a very minimal task, and they're pretty cost effective. The next is compute. This is where we're using formal verification, physical synthesis. This is we're trying to get the most done in the least amount of time. And so we're always pushing the edge here. We were running on C5, Z1Ds came out, and now we're running on Z1Ds. We see a good benefit there. We also see a really good benefit from using i3s, especially with the ephemeral. What I do here is I use these for like scratch space, stuff that's simulation results that can be replicated. We found that the i3s with the ephemeral are very fast, provide a lot more faster simulation time. Power and timing, we see that the large memory machines are really required. We've got the X1s, of course, even the high memory machines that we've coming out with recently, R5s. And then also, we're doing a lot of emulator builds on these machines, too. GPU graphics, we use these machines for the designers that need a improved desktop running in the cloud. And then GPU and FPGA, this is mainly used for, we don't usually use the GPUs that much, but we use the FPGA instances for the IP emulation. And what I mean by that is we take an IP, a small block that can fit into our F1 instance, put it on the instance, and verify it. Verifying it using accelerated verification techniques. And we do this with our own internal development cycle. Okay, so let's touch more on Z1D because they're so important to the EDA development. So these are custom cores for us, for AWS, and they're sustained all-core frequency up to 4 gigahertz. So 6 different sizes, up to 48 vCPUs, and includes local NVMe storage. Like I said, we work directly with the team to optimize the memory to vCPU ratio, and we see about a 30 to 40% improvement. Okay, so let's talk a little bit about optimizing EC2 pricing. So I'm going to talk on this slide about what we do, and then you can kind of relate it to your own infrastructure. So for on-demand, that's where we use batch. Batch uses on-demand. We see a lot of value in being able to run a regression that has 10,000 tests anytime you want. You don't wait for overnight. You don't wait for the weekend. If you need to do it at 2 p.m., you do it at 2 p.m., you get your results back so that you can debug at 3 p.m. And so on-demand is key for us. And we use the batch for the orchestration of that. Reserved instances, we still reserve instances even though we're an internal team. We want to make sure that these instances are always there for us, for our service instances, and that just helps our kind of infrastructure administration. And then Spot's very powerful for you. I can't make use out of it like you can, but it's super powerful. If I was running an external EDA company, I would be utilizing Spot as much as I could. This is where you can get lower cost, essentially, silicon development. And there's a lot of opportunity in regressions and simulations where even if Spot is running and you're preempted, you can still make a lot of progress, I think, in the silicon development space. Okay, so let's talk more about batch. So batch is an orchestration. It dynamically provisions your instances, starts them up, brings them down, right? You give it a job definition. It could be simple, like a script. We use a container. We put together a container and we run a job through the container on the instances that batch spins up. But it does all the work for you, and it's simple. The command is right there: batch, submit job, name, job definition. This one's asleep. It's pretty easy, and then outputs your job ID. It's very similar to your LSF SunGrid engine. And so we feel that batch is very powerful for us, and we see that this is kind of the future. Storage. So I talked more about I talked about storage earlier. This is ephemeral and EBS is where we focus on our NFS, our network file system architecture. We put together a mixture of the ephemeral and the EBS, and depending on the data in the data category. EFS, we definitely see a good value for that. And then the S3 is where we want majority of our kind of data lake to be. The reason why we see that is because we feel that if we put data on S3, especially like regression data that needs to be analyzed, we see that we can benefit from all the other AWS services that are out there from analyzing this data. So that's the direction that we want to go. Visualization. So I mentioned earlier, we're moving to Workspaces. Workspaces Linux was released in the spring. It's based on Amazon Linux 2, and we feel that it's the right direction for us. It's also very important that we run all of our jobs in containers so that we can define the OS requirements as we need to, and we don't have to worry that Amazon Linux 2 is going to be supported by this tool and not this tool. If it's run in containers, we can run CentOS 6.5 for this workload. We can run 7.2 in this workload, and it all works, works well. One thing if you do attend the workshop, one thing you'll see is we also use remote desktop X11 in the workshop. That's just because we can script it really easy, and it's fairly easy to use. And so that's what we're using in the workshop. Okay, so big plug for the EDA Whitepaper. So this is your Bible or your golden ticket, right? So go and read the EDA Whitepaper if you haven't already, because they've done a great job on this whitepaper. It will help you define your infrastructure and guide you in the right direction. And we're going to just keep improving this whitepaper. So keep an eye out for revisions. Okay, so now I'd like to spend a little bit of time and talk about us more. I wanted to make sure I covered all the infrastructure, AWS stuff, but I want to talk about what we are and what we do in Amazon. So we're Annapurna Labs. Annapurna Labs was a startup that was acquired by Amazon, and we're a fabless company inside of AWS. So AWS is built on multiple small teams. They're called two-pizza teams, like small startups. And we're just another one of those small teams. We have multiple projects going on, multiple internal startup teams, multiple project lines, multiple sites. It's a global group. And we're very passionate about our projects and about our customers, internal and external. And this team supports multiple projects that you've already seen, especially if you attended the Monday Night Live with Peter. So let me talk about our journey and how we got here. So back in 2014, we had multiple teams working on semiconductors, our custom silicon in AWS and Amazon. And we acquired a team in Annapurna, and we built one big, great team. And that team has built an infrastructure and migrated down an infrastructure of running in the cloud, running on AWS. And so let me talk about how we got there, because I think the story really kind of tells maybe a common story with everybody else in the EDA infrastructure or EDA industry that wants to move to the cloud. So we first started with a team that was new and didn't have anything. And we had started with a team that had a lot of stuff. They had servers in closets, servers in rooms. They had data centers. And the team that had nothing, it was very apparent and clear that they should just start on AWS, and they did. And they moved to AWS. They built the infrastructure very similar to how they knew an infrastructure, EDA infrastructure worked in the past, and they built their projects from there. The team with on-premise wanted to scale out. They wanted to, when they needed new infrastructure, when they needed more resources, they wanted to get those resources from the cloud instead of on-premise. And so they did that. It's called the hybrid model. They took their on-prem and they scaled out to the cloud when they needed it during their development cycle. This was really helpful because it shortened that silicon development time. And it allowed for them to learn about the AWS cloud and to learn about the services that are available. And then the next stage was we decided we wanted to all go in on the cloud. We wanted to be all in on AWS. And so what we did is we took everything we've done on-premise and we moved it to the cloud. There's a lift and shift. That got us there quick. We had different teams, multiple regions, and we did an end-to-end silicon project on AWS. The on-premise infrastructure stayed where it was. We maintained that, but we moved to the cloud. Now we're progressing farther today to all in the cloud, reducing the on-prem, increasing the productivity by using native AWS services, replacing the lift and shift components with new AWS services that allow us to do things faster, and so we can improve that productivity. Batch, EFS, S3, using the latest and greatest instances. That's helped us improve that productivity, shorten that development cycle. So that's been our journey. It's still continuing, and we're still progressing, but we're learning a lot. And one thing that's great that I've learned during this journey is we can, even though we're building silicon, we're building custom silicon for AWS, we can benefit, we can help the services by giving them feedback and improving it for the EDA industry. And that's what we hope to do, is we hope to go into batch and say, this is how EDA customers will use your tool, and give them that feedback, which improves these services, and we'll continue to do that. So what were the results of our movement to the AWS cloud and working on AWS? Well, we've seen the development time reduced. We had no limits to the infrastructure resources. We scaled up when we needed to. We got the GLS machines when we needed to, those high memory machines. Faster simulations. Right when we jumped on Z1D, we saw a bump. New infrastructure functionality. We started replacing things in our infrastructure that didn't need to be manually provisioned. I'll give you one example, is databases. We found that it's so much easier to use an AWS database than manage our own, so we replaced them. A lot of tools from the EDA vendors allow you to have connect up your own database and then provide that kind of hooks to connection. And we made use of that. Faster prototyping. We found that we could create proof of concepts very quickly in AWS. If there was someone had an idea and we needed to do something about it, we wanted to try it out, we could scale out a VPC, give them something to try, and then shut it down when they're done. So develop and test some new ideas. The other thing that's not on here is we found that we had sometimes external contractors working on our projects. On the on-prem, we had to give them access. We had to let them work on our project. In the cloud, we found ways to provide them an isolated working environment where we and them can work together on their piece of their work that they're delivering to our project. And we found this very helpful. And it really helped remove barriers for the contractors too, because they got a chance to be able to scale out and not be constrained by any type of internal or on-premise resource restrictions. So let me talk a little bit about what we've done at AWS Portal Labs, and I'll touch on some of the new things too. I don't have slides for those, but I'll kind of talk through them. So the big thing was, the old EC2 instances had their hypervisor running on the host, right? And so, what we've done here is the C5 was the first instance to offload, right? Nearly 100% of the CPU now is available. And that's because we have the Nitro system. That's that little card down there. That's our Annapurna's project. So this was a very important project in our journey, and we benefited from the AWS infrastructure. The next one is the F1 instance. So our engineering team has worked on FPGAs, and we built out the F1 instance 2 years ago at reInvent was released. And we're seeing a lot of growth in this area in multiple domains. Genomics, video processing, image processing, data analytics, financial. And so this instance is a instance that's available to everybody. It's a Xilinx FPGA, and you can see here kind of the architecture of it. It uses an AMI as what's loaded on the host CPU. But we've introduced a new thing called an AFI, and that's an Amazon FPGA image. Very similar characteristics to an AMI, but the key difference is that AFI, or that AFI ID, similar to an AMI ID, represents the FPGA image that gets loaded on the FPGA. And so with the AMI AFI, on the F1 instance, you have a host FPGA image that you can load at any point in time. And so if you go down deeper into the FPGA, it's connected to our CPU via PCIe 6x16, and it has 4 DRAM controllers directly connected to the FPGA. So one of the things we have on the FPGA is a small layer of security and kind of a common interface for FPGA users. And this provides customers with very common AXI type interfaces so that they can build their hardware accelerators a lot easier. And so we've done our internal development of that shell interface is all been done on top of AWS infrastructure. So we've done the verification, the synthesis, and the place and route and all that on AWS infrastructure. Now, the user, when they build their hardware accelerator for F1, they send it to us for an ingestion. And what that does is it saves off that AFI into our secure servers so that when they're ready to load it, just like you're ready to load an AMI ID, it loads an AFI, an image. And so that service runs entirely on native AWS. It's an EDA service, essentially, down underneath. It takes a checkpoint of your design, takes our shell, and merges them together in a method called partial reconfiguration, and writes out a bit stream and saves it into our secure servers. And we do all that on top of our EDA infrastructure. Okay, so let's go into a little bit of I would say a sneak peek demo at what our workshop is what's gonna be in our workshop. And so I'm gonna talk through this demo. It's gonna roll through some scaling of using batch. It uses an F1 FPGA developer kit, AMI, what's in the AMI is a Xilinx tools. Xilinx tools come with a simulator The AMI is on AWS Marketplace, and it's free. So it's a free simulator. It simulates Verilog and System Verilog. And we are going to show how you can scale up using this AMI and run simulations on AWS. So first, let me talk a little bit about the architecture of what's being created here. So the architecture is very simple. We've taken our internal templates and we've stripped them down to this base infrastructure. And this is what we're providing during the workshop. So you've got an availability zone, two private subnets, a public subnet and a private subnet. And you've got a remote desktop server. This is your desktop in the cloud. And then you've got, in your private subnet, your compute instances that are dynamically spun up and down from batch orchestration. And then we've got an NFS and an EFS server. And this is all done by using AD for the login. So that's the architecture. This is kind of the workflow. So users will log into the remote desktop. They'll bring open once they log in and are authenticated through AD, they will log in. They will run a batch submit command, and then batch will spin up instances. Data will be saved to the file system, and the results will be completed. Tests will pass or fail, and that's how the workflow. So let's zero down a little bit farther into the life of a job in this workflow. So the jobs could be a place and route, a synthesis, simulation. Those go into batch, and the batch spins up instances. What are running on those instances? What are truly there? So this is kind of a view of that. An EC2 instance, which has a host OS, which is running a Docker engine, which has multiple containers running on top of that. And so each of those containers is running that job. Each of those containers has a mount or mounts that are accessing the network file system to get tools and to write regression results. Okay, so let's start the video. This is been recorded, and I will just kind of talk through this and how it goes. So we have a script here that runs kind of a regression. And one of the key things is in the script from our developer kit for F1 is our tools. You can see it's using Vivado 2018.2. It's bringing open the tools, and it's starting to kick off the jobs. These are, we're going to simulate 10 simulation jobs. So all of these jobs are being submitted to batch. You can see here we're going to the dashboard. So we've got 9 runnable jobs and 1 running, so one's already kicked off. And we're using the GUI here to actually show something. If we can do all this through CLI and stuff, but that would be so interesting. So we're checking to see the scaling is happening. Right now there's only 1 job. So we're looking and trying to understand what's going on. Oh, we figured out that we had desired vCPUs only at 2. So we need to update the desired vCPUs to make the scale go out farther, so to go wide. So we're looking at some CloudWatch monitoring to see what our CPU usage is to make sure that our jobs are running. And so while we click through this, the FPGA developer kit is on GitHub. This demo is using a combination of the FPGA developer AMI on Marketplace and the FPGA developer kit on GitHub. So those two together, we're running one of the simulations that's in the developer kit using the Xilinx XSim tool. And these are purely just simulations of a design that is going to be on F1, but the purpose is trying to understand what are the issues before we build for F1. Building for F1 takes 4 hours plus, depending on your design complexity. So using simulation can be very helpful in working out any bugs before committing to that long build time. So now what we're going to do is we're going to change the width of this regression cluster. And we're going to do that by using desired vCPUs. We're going to change it to 20. That just made the cluster go out by about a magnitude. So we were only running one job. Now we're going to run 10 jobs. Each job takes 2 vCPUs is what the requirement here is. Okay, so now we start to see the scale out. So the instances are starting to spin up. The jobs are running. These jobs take 10, 15 minutes. We're not going to wait for this to fully complete, but you can see that the runnable jobs are now at 7, and we're starting to ramp up. Now the great thing about batch is you can set these thresholds. So you can keep so many of them instances warm so that this startup time can be very quick. That's probably some of the most important parameters that you have to kind of play with is what's your go wide size and what's your kind of your warming, which ones, how many you want to keep warm and pay for. And so that's something that is all project dependent and that you have to kind of dial in. And you can see we're kind of already starting to ramp down. So only 4 running. And we're starting to see some of the CPU usage peek through. So on our workshop, what we're going to do is we're going to use some tools called a service called CloudFormation, and we're going to provide a CloudFormation template where you'll be able to build out an EDA infrastructure right out of the box, learn about it. You get to ask the experts that built the template how you can customize it and start using it during the workshop. And you'll be able to run some simulations. We're also going to show the virtual desktop running in the cloud. And then we're going to show like a waveform editor running in the cloud. And so you'll get a kind of experience in running a simulation. And then, depending on your account limits, we built the workshop for the default account limits, but depending on your account limits, you can go as large as you want to try it out. Like I said, the AWS FPGA AMI on Marketplace has Xilinx tools, which are free. So really, it's just the compute cost. And so you could scale out to thousands of instances and run these tests. Okay, I think that pretty much concludes. So just to remember another pitch on the workshop. So you're just going to be able to take home an AWS CloudFormation template and see the massive scale of AWS. And so that's on Thursday, right-sizing your silicon design environment and elastic clusters for EDA workloads. Okay. Well, I'll stand to the side and answer any questions afterwards. So come on up and feel free to ask any questions to me. I can talk through them. Otherwise, we'll go and talk more at the workshop, hopefully. No, thank you.